Hello, everyone. It's me again, and we are back at it with another video. So in the last video, we discussed the notion of what an antiderivative was, and we talked a great deal about the fact that it was the opposite process to differentiation. So taking an antiderivative is the opposite process of taking a derivative or undoing a derivative. And then we concluded the last video by going through some fundamental properties of antiderivatives, namely, if I have the sum of two antiderivatives, so the antiderivative of a sum of two functions, might be easier if I write that down actually. In the last video, we established here that if I have a function h of x, which by definition is equal to f of x plus g of x, or it could also be f of x minus g of x, then the antiderivative of h of x with respect to x, don't forget the dx and the snake sign come together. You can't have one without the other. Well, this is simply just going to be the antiderivative of, so the sum or difference of the antiderivatives of each of these functions, plus or minus antiderivative of g of x with respect to x. This along with the constant multiplication property, that's what we ended up, this is where we finished at the last video. So by the constant multiplication, I mean this thing, that is, if I have some constant k, where k is a real number. It could also be a complex number for those of you who are doing specialist maths, but we're not going to worry about those in this video. Then if I want to take the antiderivative of the constant multiplied by my function f of x with respect to x, then that is simply equal to taking the constant out and multiplying it by the antiderivative of the function with respect to x. So these were the two properties that I elaborated on in the last video, and there is a little bit more detail in these in the notes, which I will provide in the description. So that's where we ended up in the last video. In this video, I want to provide an intuitive understanding of the idea of what a definite integral actually is. So definite integrals are things that we essentially use to calculate areas underneath curves. So the whole idea of a definite integral is you have a function, you want to find the area underneath the graph of that particular function. So there is an algorithm by which you can do that, and we'll go into a little bit more detail about this right now, actually. So let me just clear all of this out now. And let's go into the definition of what a definite integral actually is. So suppose I have a function, f of x. I really don't care what the rule of this function is at this point. It can be anything for what I care, but it doesn't really matter, and it does not need to have any specific properties aside from being continuous. I'll assume it's continuous for convenience, but let's call this y equals f of x. Notice how I have not specified any rule for this function. There's no equation associated with this. This works in generality. I'm working in generality here. Now, the whole idea of a definite integral is that we are trying to find the area underneath a curve. So suppose we want to find the area underneath the curve within a specific region that goes from one of the endpoints A to B. So suppose we wanted to find the area of this shaded region here. Right? This is the area in between the blue dotted lines is what we want to find. Suppose that's the problem that we are faced with. So remember, this interval is a closed interval, so A and B are both included within the endpoints of this. So we can write this as X being within A and B, with the square brackets indicating that both A and B are included within this domain, which we're interested in finding the area of the function, area underneath the graph of the function, I should say. One way we could think about working out this area is we could essentially split up this area into little rectangles, of a given width. And so the whole idea is we chop it up into little rectangles of a given width. We add up the areas of all the rectangles of those widths, and we combine our answer to give an estimate for the area underneath the graph. And the reason why do I do rectangles? Because rectangles are quite nice. We all know how to find areas of rectangles, right? You'll see that there are other ways of finding areas under graphs using trapeziums and things, but for this video, I will focus on rectangles. So what I'll do is I will split up the area underneath this graph that I want to find into little rectangles. So I'll divide them up into n different rectangles. So bear with me. So there's my first rectangle. There's my second rectangle. There's my third rectangle, and so on. There's my nth rectangle. I've split this up into n different rectangles. Now, the width of each rectangle, I will give a specific symbol to. The first rectangle, I'll give it the width delta x1. So this delta is the Greek should be a capital G, Greek letter delta. And for those of you who are interested in either physics or engineering, every time you see or maths even, actually maths more so than others, if you see the Greek letter delta in front of any variable, it just represents a small change in. You can replace this by saying a small change in. So small change in. You can think of this as saying a small change in. So if I say delta x1, you can think of this as saying, a small change in the x value that goes between these. So you can think of this as a small change in x. So, well, to make it more concrete, I'm just going to label the endpoint. I'll label the x values here, the x coordinates, x2, x3, all the way up to xn, which is just before b. Okay, so we've got delta x1, delta x2, you get the idea, delta x3, and so on and so forth, all the way up to delta xn. Now, those are the widths of my rectangle. You might be wondering, well, in order to find the area of my rectangle, I need the width and the height. How am I going to get the height? I'll give you a few seconds to think about that one. So in order to get the height, you can see that the height coincides with the actual point on the function. So the height of this rectangle, so the coordinates of this point here, where the first rectangle intersects the graph, is x1 and f of x1. So the y value that you get here is, you get that by plugging it in. You get by plugging in the x1 into this function here. That's what this is saying. And similarly for this one, x2, f of x2. Those are the coordinates of that point, and so on. So this one will be xn, f of xn. Right? So that's how you get the height. Now, an easy exercise for you to do is to find the area of the first rectangle. Find the area of the first rectangle, and then find the area of the second rectangle, find the area of the third rectangle, find the area of the nth rectangle, add all of those up, and then we'll have to take some limits, and that is how we will define our definite integral. So I'll give you a few seconds to figure out how to write an expression for the area of each of those rectangles. Assuming you've had a go at it now. The way I would go about writing the expression for the area of each of the rectangles. So for rectangle 1, I'll give you an example. So for rectangle 1, it's simply going to be f of x1 times delta x1. For the second rectangle, it's f of x2 delta x2. For the third one, it's f of x3 delta x3. Hope you're starting to see a pattern here. For the nth rectangle, it's f of xn delta xn. Right? Now, in order to get an estimate for the area of the graph between A and B, we've just got to add up the areas of each of these rectangles. So we've got to do this 1 plus 2 plus 3 plus 4 plus all the way up to n. So the way this is going to look is just going to be like this. So I will call the total area A. That's going to be given by f of x1 delta x1 plus f of x2 delta x2 plus f of x3 delta x3 plus all the way up to f of xn delta xn. Yuck. Does not look particularly pretty, but hang on a minute. Bear with me. We will simplify this a little bit. So this is the total area that is between A and B. Actually, this is not strictly exactly equal to the total area. This is a rough estimate for the area. In order to get a more accurate approximation for the area, in order to get a more accurate value for the area, there's a couple of things we can do. We can either decrease the width of each of those rectangles, or we can make the width smaller. We can make the rectangles narrower. That way, our widths are much smaller. We can fit in more rectangles and therefore obtain a more accurate estimate for the area underneath that graph. We can either shrink the rectangles. So suppose we have something like this. So you can make the rectangles narrower, or you could fit in more rectangles. So and you can fit more rectangles. So you can actually shrink the rectangles, make them narrower, and that'll allow you to fit in more rectangles, so that the more rectangles you have, the more accurate your estimate for the area underneath the graph will be. So essentially what this is we can express that as, we can write some limits in order to quantify that. So remember, we can make the width extremely narrow. So the smallest our width can be is 0. We can't have any negative widths or anything like that. We can't even have a 0 width, but we can have a limit that our width tends to 0. So we can write that out mathematically as limit as delta x tends to 0. I will make this more precise in a minute, of this expression A. So that's one thing we can do. If we make our widths narrower, then we can fit in more rectangles into that same space, right? Just like if you had less liquid in a jar, then you can fit in more liquid, if you know what I mean. If you drink half of a liquid in a jar, you have room to fit in more liquid. So the narrower you make your rectangles, the more you can fit into that same space. So that's one thing you can do. You can you can make it narrower, and then you can also fit in more rectangles. I've said the same thing over and over again. So limit as delta x goes to 0. And you can also take, because we had n rectangles, if we fit in a large number of them, it means that n becomes really, really big, which means that we need to take the limit that n also goes to infinity. So the largest number of rectangles that we can fit is the limiting value that we can fit under that same area is going to be infinity, right? So we can take n to infinity. Now, we've got to be a little careful here. Delta x, well, you might be wondering, what is delta x? You've labeled delta x1, delta x2, all the way up to delta xn, but what's delta x here? Now, delta x, I will define this as the width of the largest rectangle, the width of the widest rectangle. Width of the widest rectangle. Why did I choose it to be the widest rectangle? Well, think about it. If I take my widest rectangle, the one that's really, really wide compared to the others, and I take the width of that, take the limit of the width of that to go to 0, well, then every other rectangle is going to have a smaller width than this. So automatically, all the other rectangles' widths are going to go to 0 as well. So that is what I mean by delta x. So this is, by definition, the width of the widest rectangle. So if I take those two limits, my expression then becomes limit as delta x goes to 0 and n goes to infinity. I'm going to put in the expression for a here that I have. So I'm just going to copy that. Copy, and let's paste. Oh. Okay. And that is actually the definition of an integral, of a definite integral. But hey, this is nasty to write out, is it not? It's disgusting. Look at it. Imagine every time you find the area under a graph or do an integral, you have to write these out. That's gross. So in order to circumvent that, so to get around that, mathematicians define some sort of a convention. They have defined this, they define this as the following. So this is equivalent, I should say. This is by definition the definite integral, which we can write as our snake symbol, which is similar to what we saw for antiderivatives. We'll see that the two are connected in a moment. Antiderivative symbol comes with dx. And then on top here, we need to have some limits over here. So up top, we're going to have the rightmost endpoint of this region that we want to find the area here. In this case, that's B. So the top endpoint is going to be B, and the lower endpoint is going to be A. And within this integral, the thing we are within this integral goes the function f of x, which is the one that we want to find the area underneath. Okay, so this by definition is the definite integral of f of x from x equals a to x equals b. So this is the this is read as the definite integral of f of x from x equals a to x equals b, right? So this is a definition. The key word is that it is a definition. There's no way to sort of prove this. There's no way to prove that this area is equal to that. It's just something that mathematicians have defined to make things easier for them. Imagine having to write this out each time you want to do an integral. Yuck. No. So this is just easier to write down. So it's a simplicity of notation. Right. So there are a few things you can do with definite integrals, just like you could do with antiderivatives, the properties of antiderivatives. Definite integrals also have their own properties. So we'll work in generality here, and then in the coming video, I will discuss something called the fundamental theorem of calculus, which we can then use to actually evaluate these integrals. So I'll go through the fundamental theorem of calculus in the next video, and then we'll apply it to some actual functions. But for now, let's just discuss the properties of definite integrals. Properties of definite integrals. So remember, in all of the stuff that follows, an expression that looks like this is simply read as the definite integral of f of x from x equals a to x equals b. That's the idea. So these properties that I'm about to describe here, they apply to any function f of x. It doesn't really matter what function you use or what endpoints you use. It's simply it holds for any two functions as long as they are continuous. Any function that's continuous. So these hold for continuous functions. I will have to introduce two functions here, so I'll call them f of x and g of x. Hold for any two continuous functions. Continuous means that you can sketch a graph of that function without lifting your pen off the paper. That's one way to think about it. I'll actually write that down once I've written this. Functions. F of x and g of x. Right. So continuous just means I can draw this function, draw the graph of it without lifting my pen off the paper. Pen off the paper or pen off the screen, whatever you want, or the board even. But yes, you can draw it without lifting your pen off the paper. Cool. So as long as my two functions, f of x and g of x, are continuous, I can, the following properties, which I'm about to describe, they will hold. So if I have a function, f of x, if I have the definite integral of a function of x, of f of x, from x equals a to x equals b, this is equal to putting a minus sign here and then swapping the two limits. So going a on top and b down the bottom. So what that means graphically is that if I want to find the area this way, if I want to find the area of the function going from this way, from here to here, going from this function to there, it's kind of going from this endpoint to that one, going from left to right. It is equal to the negative of going from finding the area of this function from here to there, from right to left. So that's kind of a long way of saying I can swap the two limits of integration, as we call these. So this b and a are what are called limits of integration. Limits of integration. Right? A and b are what are called limits of integration. So you can think of this as saying, every time I want to swap my limits of integration, I just need to put a negative sign in front of my integral. That's it. So that's the first property. The second property that I want to describe, there are a total of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 properties here. The second one is the following. If I have the definite integral of f of x dx from x equals a to x equals a, that by definition is 0. And I encourage you to think about why that's the case, right? Think about it. If you just have one point here, a, and you want to find the area of the function, the area underneath the graph between a particular endpoint and that same endpoint, well, then the rectangle that you get, if you split it up, is not going to have any width, right? The rectangle is just going to have 0 width, which means the area of that rectangle is going to be 0. So that means that the area underneath a function, f of x, at a particular endpoint is equal to 0. Right. So this is the second property. The third one is this. If I have a constant, c, and I want to find the definite integral of that between b and x equals b and x equals a, well, this is equal to c times b minus a, where c is a constant. So you might be wondering, wait, why the hell does that come about? Well, I will describe that. Hopefully it'll become a bit clearer when we cover the fundamental theorem of calculus in the next video, but where c is a constant. The next property that I was going to go through here is the following. If I have my constant c is once again a constant, and I multiply, if I want to find the definite integral of a constant multiplied by my f of x function, well, I can evaluate this by pulling out the constant and finding the definite integral of f of x with respect to x from x equals a to x equals b. So that's what that means, right? So most of these properties will make sense once we go through the fundamental theorem of calculus. C is once again a constant. Okay, so those are the first 4 properties. Here they are. You can, if you swap the limits, you can you introduce a minus sign. The integral of a function between a particular endpoint and that same endpoint is equal to 0. Integral of a constant between 2 endpoints is just going to be that constant multiplied by the differences between the endpoints, and then a constant multiplied by your function. If you want to take the definite integral of that, then you have to pull the constant out and then multiply that by the definite integral of the function with respect to x. The next property is the one where I need to introduce another function. So if I have the definite integral between x equals b and x equals a, sorry, x equals a and x equals b of f of x plus or minus g of x, this can either be the sum or the difference of the two functions. Well, if I have the definite integral of the sum of two functions, it's just the sum or the difference of the definite integrals of each of them. So this is just by definition f of x, the definite integral between x equals a and b of f of x dx plus or minus, depending on what sign is over here, the definite integral from x equals a to x equals b of g of x with respect to x. So this is the property here. All right, so that is the fifth property. We have another property here, which is probably best illustrated by a graph. So let me just plot my function again. Give me a moment. So we've got so to illustrate the sixth property here, I'll just draw up my set of axes here. So this is sorry, I'll call this f of x just to be consistent, but f of x, x, and let's say my function looks something like this. Once again, I really don't mind what shape this function has or the equation of it. I'm just illustrating this in general. So if I want to find the definite integral of this function, so if I want to find the area underneath this function, underneath the graph of this function, between x equals a and x equals b, sorry, I'll call this c, and you will see why, pun not intended. You'll see why in a moment. And now let's suppose I have some point b that's sort of in between this. It doesn't strictly have to be halfway between those 2 points. It can just be somewhere along here. So if I want to find the area of the function, the definite integral of the function f of x between x equals a and x equals c, so this is, c is my upper limit of integration, so that goes on top, and a is my lower limit, so it goes down the bottom. If I have this, if I want to find the definite integral of my function f between x equals a and x equals c, well, you can think of this as having the total area underneath the graph between a and c. So that you can think of as finding the area of the function in this green area, in this green region here, and then adding to that the area underneath the yellow region down here. So the green integral, the integral for the green that represents the green region is the definite integral of the function f between x equals a and x equals b. And then I need to add to that the area of the yellow function plus x equals c to x equals b of f of x. And I forgot my dx, but here it is. So that is the last property of this of the definite integral. So this is what it is. So the last property is written as follows. So the definite integral between a and c of f of x dx is equal to the definite integral between x equals a and x equals some point b, which is in between, which is within that interval between a and c of f of x dx plus b to c of f of x dx. So this is the last property. And actually, this is one of the properties which is very often misunderstood or overlooked by many students. So I would highly encourage you to pay attention to stuff like this, because the VCA examiners seem to love quizzing people on this property of integrals. So I'd highly encourage you to keep this in mind while you're doing problems. With regards to problems and examples and things, I know this was a very conceptual video, and that's how I intended for it to be. But in the coming videos, I'm hoping to go through a few more worked examples. Certainly in the next video, I want to go through the fundamental theorem of calculus, which links the idea of an antiderivative and that of a definite integral. And then in the following videos, I want to go through the applications of integration. So things like the average value and the area between two curves, and kinematics and motion, which will have a lot of problems associated with those. So please stay tuned. If you have any questions or concerns, please feel free to let me know in the comments below. If you have any suggestions on how I can improve these videos, please do let me know as well, because I'm just starting out, and I'd really appreciate if you guys could let me know what you think. If you feel like something is working well, something isn't working as well, please do let me know in the comments, or feel free to shoot me an email as well. All right, that's it for this lesson. If you have any questions, please let me know in the comments below. I'll see you in the next one. Toodles.